At this point, I would like to introduce Rolf Halden from Arizona State University, and he's going to be talking about his ESTCP project ER-201122 that was on cost-effective, ultra-sensitive groundwater monitoring for site remediation and management. Rolf, I'll turn it over to you.
Thank you, Andrea. Hello and welcome everybody to the final debrief of our project 2011-22. And it's a pleasure to present today. And you will hear about an integrative sampler that we deployed in 2 different locations for organic and inorganic contaminants. So my name is Rolf Halden. I'm the PI as well as the director of the Center for Environmental Security at the Biodesign Institute. And before we start, I'd like to send out a big thank you to Andrea Leeson and the entire ESTCP team, as well as the review board and the capable staff that has supported us over the course of the last 3 years. I also like to thank our co-presenters. We're looking at slide 2 now. So we had support by Aaron Driver, a PhD student who has helped us for the past year. And then really the person leading this project is Isaac Roll. He's a PhD candidate. He will graduate here in October of 2015 with a PhD in environmental engineering, and he's looking forward to join the professional workforce. Maybe you have a place for him, and I would like to hand it over to Isaac.
All right, thank you very much, Rolf. So as Rolf said, I'm Isaac Roll. I will be presenting most of the talk today, but Rolf will also be around and will be chiming in to add some details wherever he sees fit. If we would like to move on to slide number 3. Just a little bit of background and rationale for the project that we undertook. When we proposed this project, one of the things we were looking at was the fact that there's about $8 billion spent annually in the United States on site remediation. So characterization and monitoring drive about 25% of the overall site remediation budget in the United States. There are federal mandates to reduce energy use, to reduce carbon emission, to, in general, improve the efficiency of the programs that we have, and in general, one of the things that we're trying to do with this project is to support that sort of greening of the science, as well as improving the data that we derive from our characterization efforts, and in general, improving the cost effectiveness. Moving on to slide 4. To support these challenges, we proposed a system for water sampling that applies solid phase extraction in situ. So what we are doing here is taking off-the-shelf, commercially available sorbent media, pre-packed in disposable columns, and we provide a programmable autonomous pumping system that delivers water from the environmental compartment to the sorbent cartridge, collecting all of the analytes that we're interested in the sorbent, and rejecting the rest of the water to the environment. By doing this in sort of a robotic mode as we are here, we're able to produce simultaneous replicates. We're able to program the pump to take long time integrated average samples. We're able to reduce the amount of hazardous waste and, in general, the amount of material that leaves the contaminated site. And we're able to reduce the transportation costs that are associated with moving all these water samples from the site to the laboratory. Slide 5, we see a few images of the sampler that we developed actually in action in the field. In panel A, we have the pump as it was developed. So we have here a programmable motor driving 6 syringe banks to deliver a channel of fluid to each of our sorbent cartridges, so we can take 6 simultaneous samples here. In panel B, for the development of the device as we were doing it, we needed to do some quality control and assurance on the amount of water that we were pumping, so we included a separate liquid capture system, which is what you see in panel B. In panel C, the entire system, the pumps, the solid phase extraction cartridges, and the liquid capture system have all been loaded into a stainless steel casing. And here I'm actually connecting the power and control support cables to the submersible. And then in figure D, the entire submersible has been lowered into the well, where it is taking a long time average sample by collecting small amounts of water over a long period of time, which we'll be talking about later in the presentation. Rolf, do you have anything to add?
No, slide 6.
All right, continuing to slide 6. The technical objectives for this project were to demonstrate field acquisition and in situ extraction of analytes from groundwater. So in other words, to show that we could field prepare our samples using solid phase extraction in an autonomous sampler. We wanted to demonstrate that we could eliminate the need for any human liquid sample handling and remove the entire generation of groundwater waste. We wanted to generate time-integrated average concentration samples, and we wanted to demonstrate that we can show good agreement between our sorbed samples and samples that are taken using conventional means, that is to say, by liquid sampling. On slides 7 and 8, we have the, advanced it a little bit too far here. On slides 7 and 8, we have the performance objectives from the project. I'm going to go through these quickly because we will actually be revisiting them in great detail later on. On slide 7, we have the quantitative performance objectives. The first one was demonstrate, as I said, agreement with the current methods, so to show that our sorbed samples are in good agreement with liquid samples. We wanted to demonstrate our time average sampling capability. We wanted to demonstrate operability of the instrument under conditions of high turbidity. One of the concerns leading into this project was that our commercial solid phase extraction cartridges could become occluded when used with environmental waters. So that was a key performance objective. On slide 8, we have our qualitative performance objectives. These were to demonstrate favorable labor requirements. We wanted to show that our system was no more difficult or time-consuming to use than any of the current methods. We wanted to demonstrate the utility of low method detection limits by pre-concentrating our samples in situ. We were going to provide improved method detection limits. We wanted to demonstrate reduced generation of hazardous waste and favorable cost economics. And as I said before, we will be revisiting all of these performance objectives in detail later in the presentation after we go through the demonstrations that we performed. In support of the project, we have 2 official demonstrations that were carried out. The first one I'll discuss now. It was
slide 9.
Excuse me?
On slide 9.
Yes, sir, on slide 9. So on slide 9, the first of our 2 official demonstration sites, this one was closer to our headquarters. It was at the former Williams Air Force Base in Mesa, Arizona. Our analyte target at this site was naphthalene, the polyaromatic. The site itself was a former fuel storage site that's been impacted by a significant amount of jet fuel that was spilled over time. This is actually a fairly deep contaminated site, so there are alluvial aquitards that are fairly deep underground. The uppermost aquifer is at 150 feet below ground surface. Here we were going to compare the sampling for fuel components with our in situ sampler, our automated solid phase extraction machine. Samples taken with a baler and samples taken by the site remediation contractors using a bladder pump. On slide 10, we have the basic layout of our test design. For each of the tests that we performed in support of this project, we began with method development in the lab, where we designed a solid phase extraction method that we could move to the field. We then performed baseline sampling and characterization activities so that we would have a complementary data set to compare our sorbed sample data with. And then we performed a sampling test with the in situ sampler. At former Williams Air Force Base, we used a Strata styrene divinyl benzene resin from Phenomenex to adsorb our naphthalene target sample. We took baseline samples with a bladder pump. Actually, we used reports of the concentration for naphthalene and other analytes from the site managers. Those were taken at 215 feet below ground surface using a Solon bladder pump. And we did our own sampling at 155 feet with a disposable baler. The in situ sampler, our automated system, took 3 250 milliliter composite samples over 24 hours. So these were a time integrated average sample of the concentrations over that period at a depth of 200 feet below ground surface. On slide 13, we have the results of our sampling study. For naphthalene, we found that our reported concentration was similar to that reported by the baler and the bladder pump. One of the most important things that we were able to show here was that we were able to improve the actual reporting limit by about tenfold for naphthalene. So by pre-concentrating our analytes in situ and only returning the sorbed sample, we were able to deliver a significantly larger quantity of the material without bringing all the water back to the base. Since we had these samples already taken and the styrene divinylbenzene resin is capable of collecting a variety of compounds, we went ahead and quantified a few other fuel components from the same samples. And the lower panel on slide 13 is the results for ethylbenzene and isopropylbenzene. Here we see some differences between the bladder pump samples, the baler samples, and our sorbed samples. And these differences are probably a result of a variety of factors. But one of the things that we found is that we had to sample at different depths with each of our methods. So there may have been some differences as a result of that. There may have also been some differences due to affinity for lighter molecules with our sampling resins. But we were able to get in the same range for the lighter molecules, and we were also able to once again show that we were capable of improving the reporting limit by pre-concentrating the compounds in situ. Okay, moving forward to slide 14 at our second demonstration site. Here we have another compound that we were looking for. At Williams Air Force Base, we were working with organic chemistry. So at Naval Air Station North Island, we went and worked on sampling an inorganic contaminant, in this case chromium-6, which was released into the aquifer as a result of metal plating activities at the Navy base. The underlying aquifer here is very shallow. It's a freshwater lens in a very highly permeable, sandy sort of geology. The water is at 4 feet below the ground surface. We suspected that there could be diurnal changes, so daytime shifts in the concentration in chromium-6 as a result of, for example, tidal forcing. So we proposed a 28-day integrative sampling of chromate. Once again, our method development is characterized by 3 basic steps. The first was to perform to generate a solid phase extraction method in our laboratory. So here this is on slide 15, we developed an SPE method using an ion exchange resin to capture chromium-6. We then went to the site and performed a baseline sampling series where we actually installed an autosampler to take liquid samples every 2 hours for a 24-hour time course so that we could see if we could demonstrate these diurnal concentration changes. And finally, we returned to the site with our in situ sampler and took a long time average sample. Slide 16, a few more details about our baseline and our later sampling effect. So the baseline sampling was taken at 15 feet below ground surface. This is again in a very shallow freshwater lens on North Island. Our in situ sampler with our long time integrated average samples was taken in the same well at the same depth and actually taken accumulating samples at the same rate. So samples were taken on 2-hour intervals. It's just that with our sorbent sampler, we were able to take many, many more samples, so a total of about 340 samples over 28 days as opposed to the limited number of samples that we could take with our liquid autosampler. With our in situ sampler, we were able to take simultaneous liquid and solid phase samples. Because we have a multi-channel sorbent sampler, we were able to use 3 of those channels to collect liquid samples and 3 for solid samples. So again, for quality assurance, so we could show a good agreement between our liquid and solid samplers. On slide 17, we have some of the results from our deployment at Naval Air Station North Island. The upper panel shows the result of our baseline study, which took liquid samples every 2 hours over a 24-hour time period. we were able to demonstrate that there is a diurnal fluctuation in the chromium concentration in this monitoring well over 24 hours, and that there was good agreement between the chromium concentration and the tides that were recorded in San Diego Bay. So this is an indication to us that grab sampling, particularly sparse grab sampling, such as is often performed at sites under remediation, has a significant amount of error that may be associated with it due to simple time-dependent changes that can't be caught with a single grab sample. So this provides some impetus for our argument for taking longer time average samples. From our sorbed samples, we were able to get 75% recovery of the chromium that we also saw in our liquid samples. This was in good agreement with our bench recovery for the same method. By doing our in situ pre-concentration, we were able to lower the reporting limit for our samples about 8-fold versus the laboratory reported reporting limits. And we were able to take 420 grams per sample of water and reduce that to a 4-gram solid sample that we returned to the laboratory. If we were to carry out this sort of sampling over a large number of wells or over a larger monitoring regime, we would be significantly reducing the amount of pure mass that is removed from the site, contaminated mass that then has to be disposed of later. Our time integrated average gives us an average that accounts for all of the highs and the lows of the diurnal changes in concentration, as well as any seasonal changes in concentration that may have been occurring. So we think that provides a good basis for developing the kinds of mass fluxes and other data, downstream data, that is then used for driving remediation.
Thank you, Isaac. I'd just like to chime in here and maybe define what you refer to as liquid and solid sample. So it has to be clear that we are always sampling a liquid, which is the groundwater, but for this demonstration, we not only extracted the groundwater in situ and arrived at what we call a solid sample, in the sense that all the analytes are captured on a solid phase extraction cartridge, but also we captured the liquid that entered the device in these, what you can think of like an IV bag, where the water was stored over the period of time the deployment went on. And it's important to understand that we collected the water because if you take single grab samples, you would not really be able to judge whether the sampler is actually accurately capturing the groundwater chemistry. The grab samples would define the chemistry only at one particular point in time, but the sampler draws water over an extended period of time, over days or weeks, and therefore we collected the water as well, and that's what we refer to as liquid samples collected during this validation study. Isaac?
Thank you, Rolf. Okay, so that concludes our demonstrations. Now we're actually going to move forward into addressing the performance objectives that we showed you earlier. Our first performance objective, first we'll do the quantitative objectives. Our first objective was to demonstrate agreement between our solid phase extraction samples and the liquid samples that would be taken with a baler or with a pump or with other conventional methods. And in this case, we found about a 24% difference between our liquid and solid phase samples. So that's due to the recovery from the solid phase extraction. This was within our goal of a plus or minus 30% values. And actually, if we corrected our values using the recovery that we knew a priori, our difference is only about 4%. So in this case, we were able to show good agreement between our liquid and solid phase samples. Our second performance objective was to demonstrate time-integrated average sampling capability. And again, at Naval Air Station North Island, we were able to take a time-integrated average over 28 days with a concentration that we were able to show was in statistical agreement with our liquid samples that were taken at the same time. We compared them with a t-test and found that the mean concentrations were indistinguishable.
And these data are captured on slide 19.
Our third quantitative performance objective was to demonstrate operability of our sampler under environmental conditions, so conditions where there could be high turbidity. We were able to demonstrate that the liquid sampling channels and the sorbed phase sampling channels were able to collect volumes of water that were that the mean volumes were statistically indistinguishable. So the cartridges did not become occluded significantly and did not prevent water from being collected in those channels. So this was considered a success for the quantitative performance objective here. Our channels were identical.
Moving on to slide 21.
We have 4 qualitative performance objectives, the first of which is on slide 21, and that was to demonstrate favorable labor requirements. To do this, we qualitatively compared the amount of time required to install and deinstall our in situ sampler versus the time and labor required to use other conventional methods and techniques. And what we found was that the amount of field labor required to install this system was pretty similar to other mechanical autosamplers. For example, the liquid autosampler that we installed for our baseline study. So in this case, we were able to demonstrate that the labor requirements were actually broadly similar for all of these devices. Our second qualitative performance objective on slide 22 was to demonstrate the utility of low method detection limits. Here, in both of the demonstrations that we provided, we were able to show, in the case of the chromium study, we were able to demonstrate reporting limits that were 8 times lower than sampling without pre-concentration. And in the case of the organic sampling, we were able to demonstrate reporting limits 10 times lower than liquid sampling without pre-concentration. So here we were able to show that in the case where if this sampler was deployed in a well where the actual concentration of the contaminant was below the method detection limit for other methods, we would actually be able to provide qualitative data for that same analyte. On slide 23, our third performance objective, qualitative performance objective, was to demonstrate reduced generation of hazardous waste. At our first site, we reduced 250 ml samples to about 4 grams, and at the second site, we reduced 400 milliliter samples to 4 grams. So we were able to significantly reduce the volume and mass of hazardous material that was removed from the site. The operational waste, however, due to the logistics of deploying at our 2 sites, we had to commingle a lot of the decontamination water and consumables for our in situ sampler, our demonstration sampler, and also for our conventional methods such as using balers. So we weren't able to quantify the sort of normal operational waste that any sampling method would use, gloves and trash bags and that sort of thing. But for our actual groundwater waste, we were able to meet this objective and show that we could significantly reduce the amount of waste that is removed from the site. Our final qualitative performance objective was to demonstrate favorable cost economics, and for that I'm actually going to move forward into the next part of the presentation, which was a basic cost analysis for the device. And here we were able to actually show that the per sample costs for the in situ sampler are comparable or the same as those performed using conventional methods. So on slide 25, we have the 2 cost models that we generated for this project. In the upper panel, we have the capital cost model. This is the amount of money that is required to build one of our research model samplers. So these are, as you can imagine, highly adjustable devices that were made by hand in our machine shop. And the unit cost for one of these samplers, as the ones we're currently working with, is about $4,000, which on the next slide, when I switch over to that in a minute, we'll see is broadly comparable to most similar devices that are on the market right now. Our operating cost is broken into 3 parts. The first part for our operating cost is the actual operation of the sampler itself, the per sample costs that are associated with making these sorbed samples. So we have our consumables such as FPE cartridges and other consumables used by technicians in the field. which will run between $1 and about $5 per sample. Once the samples are taken in the field, they have to be shipped to a laboratory that is capable of extracting them and quantifying the material on the samples. A shipping for 6 samples, a basic shipment, for example, from San Diego to Los Angeles, which is the distance that we use for our cost model, is about $40 in this case to ship the ice and the samples and the packaging. Labor for the samples to install and deinstall the sampler is about $240, and this assumed that we had 2 technicians who required 1 hour to install and 1 hour to deinstall the sampler. So the subtotal for sampling would be $280 for 1 sample or for 6 samples. So it's the same regardless of how many samples we take there. So every 6 samples would be $280. Sample analysis at a certified laboratory is about $60 to $200 per sample, and this is using estimates based on a variety of typical organic and inorganic analytes that a commercial laboratory will quantify in environmental samples. And there's one more cost item that can be associated with operating costs, and this comes to installation of our sampler in very deep aquifers. So, for example, when we installed our sampler in Mesa, Arizona, we were working at 200 feet below ground surface, and for health and safety reasons, the amount of cable and the weight of all the apparatus indicated that we should probably not attempt to do this manually, but we used a crane to install the device at that point. And crane rental ran about $1,500. So taking all of the costs and making a per sample cost, the low and high range per sample to install our device is between $110 and $500 per sample, and that's completely inclusive of labor costs. That's inclusive of all the materials and all the sample analysis, all the standard costs you can imagine. Cost comparison of our device, the capital cost versus other standard equipment. We received a lot of we actually solicited bids for several different kind of comparable devices that have capabilities that are either complementary or overlap with the research model that we developed here. And as you can see, most of these water sampling systems run in the thousands of dollars, less than $5,000, but more than $1,000. And our research model actually fits pretty neatly right in the middle with the rest of them. So we haven't developed a system that is onerously costly upfront. Actually, it's pretty efficient even for a research model. Moving on to slide 27 and ScaleUp. Since we finished our second demonstration deployment for ESCCP, we've been continuing to do domestic and international sampling with our device. The picture here is actually from some colleagues who were using this device to sample surface waters in Switzerland. The analyte spectrum, as we continue to add methods, our spectrum of analytes that we've been capable of sampling with the device has been expanding, and actually can be continuously expanded to any solid phase extraction method that's really been validated on the bench for large volume extractions. We can then apply with our device to time integrated sampling in the field. We see a lot of opportunities in moving forward from research units to commercial units. As we move towards commercialization, some of our main benefits that we see are, chances to substitute, mass-produced parts and parts that are selected for again, easy access for some of the custom machined handmade parts that we've been using. We should be able to continue to reduce the complexity of the instrument by retaining the simplest forms of the parts and kind of taking out some of the adjustable pieces that we've included as part of our research instruments. So, for example, we don't include the liquid sampling sections in our instruments anymore. We've significantly reduced the complexity of the device by removing that capability, since it's no longer needed for quality assurance. And by increasing the number of devices that are produced, a commercialization effort would probably significantly reduce the capital costs, since our one-off devices are very labor intensive. The lessons that we've learned over the course of this project, we've been able to demonstrate the ability to provide a lot of utility to current water sampling efforts by expanding the sort of information that can be developed in a groundwater monitoring system. We can provide long time-integrated sampling with extremely good precision and reduced error by taking simultaneous replicate samples. We are able to use commercial off-the-shelf consumables for a variety of analytes. So any solid phase extraction media that's been developed for specialty use, for example, for explosives or for pesticides or for various other specialized applications, can be applied to our technique. Field extraction has been demonstrated to improve analyte stability and reduce the sample weight and volume. There have been a number of studies before ours that showed that analyte stability improves when compounds are sorbed to a sorbent media, and we were able to significantly demonstrate waste reductions. One of the key lessons that we have from our work was that the SPE method development is a good predictor of the success of the instrument. So, for example, when we were deploying for organic contaminants in Mesa, Arizona, our method was developed for and applied to naphthalene, and there we found a lot of great success. The analytes that we had not pre-optimized for, the additional things that we searched for, we were able to make the method work, but optimization in the lab is key to success in the field. Moving to our final lesson learned slide, which is slide 29. Our in situ sampler technology is going to be able to provide monitoring of the whole spectrum of organic and inorganic water constituents, as long as there is off-the-shelf media available, and there is for many hundreds of analytes. The sampler embodiment that we have demonstrated was most cost-effective in intermediate and shallow aquifers, and this is again due to the sort of health and safety aspect of dealing with very large amounts of support cables and the other infrastructure that we needed. But as the device is developed further and the amount of material needed to carry out these processes is reduced, we think that it can be improved for deep sampling as well. We were able to demonstrate long-base time-integrated sampling over 28 days, and our QA and we were able to demonstrate good quality control and quality assurance by taking multiple samples for each of our deployments. Finally, we were able to demonstrate a sort of a greening of water sampling by reducing the weight and volume of the samples that we took. The last slide that we have for you is slide 30. The available tools and training that have been produced by this project. So we have 3 reports that we have generated. Our final report, cost and performance report, and our standard operating procedure are now all available and have been published. We have a webinar upcoming where we will actually be talking more about the sort of nuts and bolts of using the technique and the instrument that we have developed and how to apply it for sampling for real-world projects as opposed to the sort of the demonstration-oriented projects that we've been showing in this webinar. We also have a paper coming up that will be focused on providing a first look at the device and the method and some of the rationale and methodology around it. And in the past, we've actually submitted this device to a number of technology incubators where it has moved forward a couple of times, and we're hoping to continue to move it forward until we get it commercialized in the end. Thank you very much, and I believe we will take any questions.
Thank you, Isaac, for an excellent presentation. Before we move into the Q&A area, I just wanted to thank again all the staff at ESTCP, but also the folks at the deployment and demonstration sites. I see Michael Pound here as one of the persons dialing in. Thanks to you, Michael, and others who supported us. We know it took a significant amount of effort and time, and we really appreciate it. Also, if you don't have an opportunity to speak up regarding questions that you'd like to get answered, we encourage you to email us at Halden, that's HALDEN, @asu.edu, with any suggestions or questions, and we'd like to integrate those into the upcoming webinar. And with this, the formal presentation is over. I believe I hand it back to Andrea for the Q&A.
Thank you, Rolf. Thanks, Isaac. Really appreciate the presentation. Does anybody have any questions at this time?
I got a question. Hi, this is Hunter Anderson at the Air Force Civil Engineer Center. Have you guys given any thought in the commercial application to whether or not the multiple cartridges would be designed in series to monitor for breakthrough and cartridge saturation, or would they just be assumed that you would have to pre-calibrate the cartridge to some anticipated concentration in situ?
Absolutely, and I'm sorry that actually didn't come through clearly in the presentation before. That's one of our key design elements, is that we do breakthrough detection by series sampling. And in addition to doing breakthrough detection with series sampling, we can actually do series sampling with different classes of sorbents. So for example, an ion exchange sorbent could be followed up by an organic, lipophilic sorbent, for example, so that we can do analyte separation in situ as well, and then the optimized cartridges for each one can go to separate extraction and quantification routes. So yes, series sampling is certainly one of the things that we have been looking at and working with a lot.
Yeah, okay, great. Because, presumably if you were monitoring some source zone and you wanted a longer duration sample for whatever reason, I guess theoretically there would be a limit you could calculate, and as long as you were within that upper bound, you'd be fine, huh?
That's right. And if you're interested in quantitative measurement, then certainly having the quality control of a breakthrough control is very important. We can also think of a scenario where the device is being used solely as a sentinel device, where we may not care about quantifying the analyte on the cartridge just to detect or non-detect. In that case, an even larger amount of water could be run through it, since we're solely looking at a detect or non-detect sort of scenario. Thank you.
Gotcha. Yep. Thank you.
Hello, this is Tom Georgian with the Army Corps of Engineers. Why did you use the t-test to compare the data sets? Were the sample sizes too small to use any other technique, or was everything normally distributed?
Hi, thank you for the question. We used the t-test for simplicity, and we made the assumption that the sample sizes were normally distributed. The sample sizes were very small, actually. In this case, we only had a handful of samples to compare, so we weren't able to do any very sophisticated comparisons there. We just wanted a simple demonstration of equivalence of the means.
Any other questions?
Hi, Andrea. This is Ralph. Great presentation. This is Marvin Unger from the program office. Not a question, but a comment. If you have any write-ups or anything that indicates where the IS-2 is being commercially used or has been commercially used, if you could send that to the program office, that would be great. And if you have any videos, short videos or the likes, of how to install it, what it looks like, etc., we'd be interested in that also.
Thank you, Marvin. Yeah, definitely. I think we have quite a bit of footage, maybe some video footage of how to put pieces together, but also a lot of photographs of the deployment. So the instrument, we filed a patent early on for this technology, and it's being reviewed by the patent office. I believe the application is published, so you can look it up. It is available for licensing the technology for anybody interested. But yeah, we encourage you to contact us here. Also, Arizona Technology Enterprise, AZTE, that handles all the IP for Arizona State University, and we'd be happy to make available all the material to enable folks to understand what it can and cannot do. Thanks.
That would be great. Thank you, Ralph.
Any other questions? Okay. Well, thanks again, Rolf and Isaac. I appreciate you taking the time to give us this debrief today. We do appreciate it. It's very helpful to the program to get a final summary of the project. And we will work to get that posted on the website so others can see it too. Thank you.
Thanks, Andrea. It's been a pleasure, and we'd like to thank everybody who dialed in. And again, encourage you to email us if you have questions. We'd be happy to address them either individually or possibly in the upcoming webinar. So stay tuned. Thank you.